This is the second of the data types, talks looking at primitive data primarily within C++. I'm going to explore sort of a mixed bag of content within this talk, from casting to structs to arrays, lots of sort of miscellaneous things about data types, but nonetheless useful, I suppose, by way of understanding some of the characteristics of how primitive data works, is structured, is accessed within C++. We'll start off having a look at arrays. And when we think of an array, I mean, again, I'm going to assume you already know what all these things are. Basically, an array, yes, it's a structured form of data. I'm going to set aside sufficient memory to hold a defined number of copies of a particular base type. Look, we can do that for complex data, for classes. We can also do it for primitive data. And you can see a couple of examples over here where we are initializing an array of ints and one of chars. And also a few examples by way we are assigning values to it. And some of the miscellaneous stuff in terms of how C++ works, there's a whole bunch of rules about how you can assign these things to it. And if you assign fewer parameters than there are available spaces, so for example, we had an array of, say, 5 ints, and we only provided 3 of them, then it's the first 3 that get to be specified, and whatever default values you have in place for the remaining ones. C++11, it also enriched it to add in a few other forms of initialization, including a fairly good or a fairly common mechanism whereby you can initialize, set all the values to 0 within the created array. We will be looking at multi-dimensional arrays, 2, 3, however dimensions you want, and you can see a few examples of actually populating a 2 by 3 array over on that side. Arrays in C++, I mean, but when we look at pointers, we're going to see that pointers offers a particularly powerful way of processing and manipulating the content of arrays. There are different ways of constructing them. You can see a few examples over there. One at the bottom, I think, is quite pertinent, because there we have a 2 by 3 array, but we are constructing it using a single list of numbers. And that gets at a fundamental truth within this here, that anytime we create an array, what we are doing is we are setting aside, reserving a chunk of memory capable of storing sufficient, whatever it is, within that particular array. So we may be doing a 3, a 4, or 5 dimensional array, but under the surface it will be stored as a single one-dimensional strip of memory. And any particular location within that one-dimensional array, we can map it onto a corresponding array location. And likewise, if I have a set of indices, I can then map that onto a particular location in my one-dimensional array. And that relationship is quite important. You see an example sort of graphically on the right-hand side of the screen. As mentioned, when we do look at pointers, we'll see that they offer us a way of jumping through the array and stepping through it in different ways. Next up then is casting. Casting is the process, again, I'm assuming you're going to be aware of this, of converting from one data type into another data type. There's actually quite a few different ways of doing this in C++. C++11 put in 4 different casts. And the old style C++98 had sort of 2-ish. And they're dangerous casts, and we'll look at them shortly. And C++11 tried to do it a little bit more safely. So they've explicitly defined 4 different types of cast. They look a bit ugly, and when you see them in code, to my mind, they're nowhere near as elegant, for example, as they ought to be. But they actually are quite good. They do permit the programmer to precisely say how it is he or she wishes to cast from one into the other. So you've got a nice balance just in terms of ease of use, compare it then with the ability to be precise in terms of what it is you want to achieve. So they are static cast, const cast, dynamic cast, and reinterpret cast. When we're looking at classes, we'll look at these in more detail. I only want to look at one at this point in time, a static cast, which is, as I say, is applicable in most ordinary situations. Most meaning that if you're dealing with primitive data, then this is probably the one you want to use. Static in this case means it is done at compile time. It is a compile time cast as opposed to a runtime cast, which can be of use when we're dealing with classes and casting up and down through hierarchies. Basically what static cast does is it takes a data of one type and gives you out as data in the other. So if we had, you see example down here for two ints, 2 and 4, double on the other side, answer is n divided by m. Now we want to avoid using integer arithmetic on the right hand side, so we cast one of the values up to a double, which will implicitly then cast the other one and then give us the correct answer on the other side. And you can see an example there of how it's achieved. The old style casts, which actually look very much like the manner of casting you have within Java and C#, though Java and C# works differently, a little more safely. You can see that over in the top right. So again, we have 2 and 4 for n and m, and we're calculating the same in lines 2 and 3, the same sort of answer, using the two old style casts. And okay, actually looks cleaner. But it is fundamentally more dangerous. And just to mention, as I mentioned in the last slide, that there is a further type which is automatic casting or type coercion. So n divided by m, if we change the bottom line into a double, there we're left with an integer divided by a double, and we'll automatically then cast that integer into a double, so we have double divided by double, and we get sort of correct maths coming out of it. Now, bit at the bottom. Recommended that the old style C++ casts aren't used, as they have little in the way of checking that you're doing things sensibly. So for the code fragment we have at the bottom, here we're declaring in line 1 a new array of doubles. So we're setting aside a chunk of memory sufficient to hold 10 doubles. And I get a pointer to this. So I've got a pointer to whereabouts in memory this array commences. In line 2, I'm saying that even though this points to an array of doubles, I want to treat it as if it points to an array of characters. So I basically want to reinterpret that chunk of memory to say that, okay, even though, yes, if somebody else is accessing it through PR2R data, they might think it's an array of doubles, I want to process it as an array of characters. Fundamentally unsafe, silly thing to do, but C++ will let you do it because it just assumes, well, if the programmer wants to do that, the programmer wants to do it. Using the new style cast, it won't actually compile. It's going to say, are you sure? You're sort of forcing a car star turning into a double pointer. Now, you can reinterpret it and force it if you want to, but at least using a static cast, the compiler will ask you to really to reflect on what you're asking it to do. So here be monsters. We're going to have a look at not at casting, that can be a sort of a source of issue, but particularly, well, actually related to casting, integers can be booleans and booleans can be integers, and just to get our head around how or some of the implications of that. So when we're looking at primitive data types, we saw that chars and bools are all types of ints or integers. So what this means is that because fundamentally they're stored as a number, in C++ you can consider an integer to be a boolean, and you can also consider a boolean to be an integer. How does that work? Well, an integer value of 0 is considered to be false, and an integer value of anything else is considered to be true. And that can give us sometimes unexpected outcomes. There's a fragment of code at the bottom of the screen. I want you to think through, well, under what conditions will the if statement be triggered? So we have integer counts equal to 2 and totals equal to 4. So we have some counter and we have some total value. And my intention is that if count isn't yet beyond total, so it's less than or equal to total, then I want to trigger some action. I want to do something. It's only when count exceeds the total that I don't want to do it. So I'm asking here that if it isn't the case that count is greater than total, then trigger the action. So what I have in mind, count's greater than total, 2's greater than 4, no, it's not the case. Right, okay, so that'll be, it's not the case, so then I should trigger it. Now, do you think that's what will happen? Do you have a bit of a ponder in terms of under what conditions you think that trigger will happen? It's maybe not, unless you are a C++ programmer, it's maybe not what you might expect it to be. But we'll have a look now in the next slide. Now, key to this, effectively in that last line, we had a couple of operators. We were doing a comparison of something greater than another thing, and we were also doing a negation. We were negating something. And for all of the operators within a language, they will give a precedence table. They will say which operator you do first, which is higher precedence, which is next, which is next, which is next. And that precedence gets to determine the order in which an expression is evaluated. And if we want to change that, then we put things within our round brackets. So fairly common. Now, what I hope you didn't forget is that negation has a higher precedence than comparison. So the statement that we had in the previous one, if not count is greater than total, and putting in the values of 2 and 4, it will get to be evaluated as, first of all, not 2 is greater than 4. That's the order in which the parser will then sort of look to evaluate that sequence. Now you might go, not 2? That doesn't make any sense at all. How can you have not 2? And you're right, you can't apply negation to an integer. It's for Boolean values. It's for true-false values. But C++ is happy to convert integers into Booleans. So C++ will do an implicit, an automatic conversion here, an automatic cast. It will take an integer value of 2 and turn it into a Boolean value. Now, 2 we know is not 0, so it's true. So it will take 2 and turn it into the Boolean value true. And we will then apply the negation to that. So not true is going to be false. So after that we end up with this particular line in line 4. So far we have evaluated our statement, and we've got that if false is greater than 4, then we'll trigger it. Again, we've got a bit of a problem because false greater than 4 doesn't make much sense. If we're looking at that greater than symbol, then we want to have it apply, in this case here, to integer data, because we have an integer on the other side. But C++ is happy to take a Boolean value and turn it into an integer. It's just numbers as far as it is concerned. So it takes a value of false and converts that into an integer. False corresponds to a value of 0. So we end up then with the expression 0 is greater than 4, which evaluates to false, so the trigger won't actually get to be triggered. And you can see there that effectively, unless we change the value of total, it's never going to be triggered. We're always going to be stuck at this particular point. And it's important then to bear in mind that sometimes, because C++ is willing to convert Booleans and chars into integers and vice versa, that you need to be careful about what it actually is doing under the surface and to break it down step by step. Next up, we're going to have a very brief look at variations in data size. Now, we already looked at this in the last talk, so I'm just going to touch upon a few other aspects in this section. As we've already seen, that sometimes a long is not that long. C++, most current definitions, long is 4 bytes, same size as an int. If it's a long, we need it to go to, if we wanted, an 8-byte integer value. Whereas in C#, in Java, longs are 64-bit values, 8-byte values longs. The only requirement in C++ is that a long must not be smaller than an int, And in turn, an int must not be smaller than a short, and a short must not be smaller than a char. So it doesn't let you do smaller one, but it doesn't necessarily guarantee that it is bigger. It's not entirely satisfactory. There are some common-ish ways of getting around this. Visual Studio has a fairly nice, you see down at the bottom, CSD standard defined int, and that includes a number of explicitly defined integer sizes, be it for signed or unsigned. So if you are using Visual Studio and you did want to use an unsigned 32-bit int, which is definitely 32 bits in size, then it provides a data type definition that you can use, and sometimes you might see that in other people's code. I'm going to have a look at structures. It says in passing here, and it very much is in passing. When we look at classes, we'll come back to structures at that particular point. The reason for this is that in C++, structures and classes, there's very, very little difference between the two. Simply to flag up a structure, what we mean is a composite, a combination of a number of primitive pieces, or it doesn't necessarily primitive pieces, but a number of pieces of data. That if we want to take several pieces of data and group them all together into one composite type, we can do this using a structure, or struct. Very useful. And you can see here a definition of a couple of them. We access it using the dot operator. It gives us a way of getting access to the individual data defined within the structure. And a little bit about declaration of it, that even if see the bottom one, we're declaring a pixel, so we have a number of different char values. Now, simple, char character, RGBA, there effectively we're using, because we want an 8-bit integer, we're using a char as an 8-bit integer in that regard. That button struct, we're not actually creating instances of it as part of this definition of the pixel, but we still must make sure we remember to include the semicolon to finalize the definition. A little bit more on this about how we actually initialize a structure. It's fairly straightforward. It is in many respects similar to initialization of a class, but we'll see that when we get on to looking at classes. You can specify a bunch of values. It assumes to be the value that you specify are assumed to populate the data types declared within the structure in the order in which they are declared. If you do provide fewer initializing values than data types in the structure, generally iffy thing to do, but you can do it, then it assigns whatever ones you have provided and sort of goes for default initialization in the remaining values, but generally not a sensible thing to do. Takeaways on this, okay, I mean, we looked at a range of different things here. Important things to bear in mind is that for chars and bools, they are integers, and C++ is very happy to convert from one into the other. In all of this, it's important to have, I suppose, an understanding of what a data type is, if a set of values, a set of operators, and then to have I suppose, the common ones that you tend to use, and to have a good idea about how they get to be manipulated and how you can safely turn one into another or to safely combine them together.